This is an experiment showing a state machine model for digital logic class. Now this board is called a protoboard, and a protoboard is used to help minimize the number of connections that you have to make, because they make a lot of the connections for you. For example, every row of 5 holes, horizontal row of 5 holes, are connected. So for example, if I look at this connection right here, this pin in there, if I put this wire in here, it will be electrically connected to that orange wire. Because again, every row of 5 is connected electrically. Now we've got these vertical rows or columns, and the vertical rows are a little bit different in that everything along the vertical row is connected. So everything along here, this red pin, this red wire, is connected to this green wire and this green wire and this yellow wire. They're all connected. In the same way along these rows here, all the vertical rows are connected. So this orange wire is connected to that orange wire. Typically on a protoboard, you connect the power up here to these terminals. Well, we're not using those terminals, so that they're not connected to the board. We're using our power through the battery pack here. We've got the red terminal, which is giving us the high voltage, or VCC, and then we've got the black lead giving us the low voltage, or the ground. So black is ground, red is VCC. So if I follow these connections, these black wires are connected over to here, and this is a dip switch, which allows me to turn on the power. If I press this button, I've turned on the power to this unit. Now, the other things that we have on this unit are chips, IC chips. These again are the dip switches. These are LEDs to show our outputs. If they light up, it's a 1, it's on. If they're off, then it's a 0. This is the decoder. This is the register chip, which is made up of D flip-flops. This is a 3-input OR gate. This one is a 2-input OR gate, and this one is a debouncer chip. It's not really part of our main logic circuit. It just helps to make the circuit work a little bit better. These are switches. This is the clock button for our state machine, and this is a reset button, this one here. Now, what I'm asking you to do is to wire this up using the state machine diagram that was given, the pin diagram. Looking at the pin connection diagram, you want to connect pin 15 from the decoder chip to pin 2 of the D flip-flop. Similarly, you want to connect pin 13 of the decoder to pin 1 of the 2-input OR gate. In the back of your handout are the pin diagrams. So this, for example, is a decoder pin, and this shows an IC, a decoder IC, with a little notch at the top. Once you see the notch, you locate pin 1 right next to the notch. It's just to the left of the notch. And then you count down along the side in sequence, 1 through 8. And then you start up the other side, 9 through 16. And the register chip is the same, only it counts 1 through 7 and then 8 through 14. And here's the notch, is up near pin 1. Looking back at this decoder chip here, there's a notch right there that you can see in that one. The other ones, their notches are just sort of inserted little dimples in there. This one has a little dimple that you can barely see in there. So all of these chips are put in here so that the notch is near the top. That means the top left pin is pin 1. So if I count with pin 1, it's right there, and in this case pin 8 is here. And then pin 9 up through pin 16. Now pin 16 is required to be connected to power, to VCC. Well, it is, because this pin is inserted in this row, and that row is connected to that orange wire. That orange wire is connected to this vertical strip here. Well, this vertical strip here is connected to red. The red wire is then connected to the high voltage. And that's true of all of these chips. All of these chips have to have the power up in the highest most pin number, and they all do. So this one has a power connected there. Now, what I want you to do is, again, follow this pin diagram. So pin 15, so if this is pin 16, this is pin 15, should be connected to pin 2 of the D flip-flop. Well, here's the D flip-flop. Pin 1 is right next to that notch. Pin 2 is there. That's the first connection. Similarly, if you want to connect pin 13 to pin 1 of the 2-input OR gate. Pin 13 that's pin 15, so this must be pin 13. It doesn't matter where I put it in that row, just somewhere in that row, connected to pin 1 of the 2-input OR gate. Well, this is the 2-input OR gate here. There's pin 1, and I connect it that way. And then you just finish it off using that form. Once you complete your wiring, it should look like this. Now there's a couple of other things that I want to show you on this. One is the operation of the dip switch. The dip switch is used to give you an input. So one of your inputs goes into pin 1. This is the external input. So if it's off, that's a 0, and if it's on, that's a 1. Now this is the on switch for the entire unit. This is the reset button, which puts it into the 00 state. This is the clock button. If I press this, it will advance the clock forward so that the state should advance to the next state given the input that you've put in there. So I just press that once. And just a little comment, there's a little bit of circuitry here and here. It's called a debounce circuit because sometimes when you push a button like this, you get a spike and a ripple effect, which causes it to think there's a second input. So we have a debouncer circuit to filter that out. But that is really not part of the lab that we're looking at. So that part was pre-wired. All we're trying to have you do is wire the logic between the different chips so that you build the state machine. You go ahead and get this working. If I put the reset, it should go into the 00 state. And right now I've got the input off. With the input off, and if I hit the clock button, it should go to the 01 state. And that is 01. Now if I hit it again with the input being 0, I should go to the next state, which is 10, state C. Now, without changing that input, if I click it again, I'm just going to stay in state C. If you follow the state diagram, state transition diagram. Now, if I change the input to 01, that's an input of 1 now, and I'm in state C, and I give it an input of 1, I should go to state 00, which is state A, and it does. So your job is to take the board that we gave you and build it to look like this. That's part A of the experiment. Part B of the experiment will be for you to take the state machine that you designed and wire it just as you wired this one. Thank you.